Okay, welcome to the Physics 163 podcast for Chapter 24. We're going to talk about sinusoidal electromagnetic radiation, its causes. We're going to talk about how to describe energy and momentum in radiation. We're also going to discuss the effects of radiation on matter. And then we'll talk about polarizers. It's a special type of matter that affects electromagnetic radiation. So to get started, what we're going to do is review some of the stuff that we did in the last class. So here, what I want you to do is come up with a direction for the radiative electric field detected at location A, and I'll give you about 30 seconds to come up with an answer. Okay, I want you to pick an answer, whether it's right or wrong, just pick an answer. So let's talk about what's going to happen to the proton at location B. When the electric field hits it, it will experience a force in direction 3. So what we need to do, if it's under a net force, it will have an acceleration in direction 3. Then we need to find the perpendicular acceleration to that is perpendicular to the distance between A and B. That perpendicular direction of the acceleration would be in direction 4. And there's the minus sign in the calculation of the radiative electric field. So that's going to put it in direction 8 at location A. I hope you can get that answer. If not, you need to go back and practice how to find the direction of the radiative electric field. On to the next question. Here we have a similar setup, except it's an electron located at A, and you want to find the direction of the radiative electric field at B. So I'll give you another 30 seconds to try to come up with the direction. All right, we're going to do the same thing we did on the last question. The net acceleration should point in direction 5. The perpendicular acceleration for that should be pointing in direction 6. And then now we have a minus charge and the minus sign in the electric radiated field calculation. So that gives us a plus sign. So the E field still should be pointing in direction 6. I hope you were able to get this answer. If not, I would review these last two questions until you can find the correct answer. On to the new information. So, what we're going to talk about is how to produce this sinusoidal radiation. And you can see this picture. And what you have is a charge attached to a spring, and we make it a positive charge. The thing is, how do we create it? Well, think of the charge attached to the vertical spring. It can oscillate up and down. And as it oscillates up and down, we can describe its position by this function. We take the derivative of the position, and we get its velocity. We take the derivative of the velocity, we get the acceleration, and we have an accelerated charge. And this accelerated charge will produce this type of electric field. If we find the perpendicular component of that electric field, we get the radiative electric field. And so this charge will also do what's called as re-radiate, information. So basically what happens is, here's your electric field that's going to come in, or the electric field that can be produced. It produces a nice sine wave, and this is why we call it sinusoidal radiation. Since it's oscillating back and forth, it does have an amplitude, and we use that to help describe the wave. In our case, it would be equal to a minus omega squared times y max. The distance between two successive peaks is called its wavelength. If you're measuring in the x direction, if you make the graph in terms of time, you can get that distance that's represented by the wavelength is also the period. It could also be the period, but the graph has to be as a position versus time graph. And you can also get a frequency. They're related this way. And you can also calculate the velocity of the wave by knowing its wavelength. What is polarized radiation? Basically, the electromagnetic field only exists along, is aligned only along one axis at a time. Unpolarized radiation the electric field is aligned along many different axes. That's why it's called unpolarized. And we'll use this later in the podcast to help us figure out what happens to polarizers. Okay, electromagnetic radiation can also store energy and momentum. The way we can figure out, let's say, the energy first, is that we know the energy per unit volume stored in electromagnetic radiation. We've represented it this way. And what I want to do is use that E is equal to C times B to help replace B and just solve it for terms of electric field. And if you do that, you get the radiative energy is proportional to the magnitude of the electric field squared. Now, what we want is energy flux, and that is defined as power by power divided by area. Remember, power is energy per unit time. Now, this also goes by a couple other names. One of them is intensity, or if it's the intensity of the sun we're talking about, it's insolation is referred to. And if we do all our calculations for the energy per unit volume and then multiply that by a volume, we get an expression that we can write out the energy flux as epsilon naught times E squared times the speed of light. Now, if we try to write E in terms again as B times C, as one of the E's, I can write it as this expression, and then the magnitude of E times the magnitude of B is equivalent to writing the cross product of E cross B and taking its magnitude. Since the angle between them is 90 degrees, the sine of that angle equals 1. So that allows me to calculate the energy flux or the intensity of a particular electromagnetic wave. Now, try to use that information to solve this problem. So we have the average power output of the sun, and what they want is the average power output per unit area for the solar radiation at Earth's location, which we know is 1.5 times 10 to the 11 meters away. And again, it gives you some other ways of looking at power divided by area, radiance, or intensity it's referred to. They want to know which one of these answers is correct. So what I want you to do is find an answer. All right, let's talk about how you get the answer. So the answer to this question is actually 2. And the way I get it is I know that intensity is equal to the power divided by area. And what area do you need to use? Well, you need to use the surface area of a sphere because the power of the sun is radiated 3-dimensionally around, all around it. And so you go out the radius r, and you imagine a sphere of that radius r that they've given you, which is 1.5 times 10 to the 11 meters, and then calculate its area, so all that power has to radiate through that area, and you come up with an intensity of 1,414 watts per square meter, and the closest answer is 2. All right, how about this equation? You have a pulse of radiation with a uniform E field of 720 volts per meter in the plus y direction. B is in the z direction. It propagates in the plus x direction. The pulse is confined to a volume of a box that's 2 meters tall, 0.8 meters wide, and 0.5 meters deep. What is the total energy stored in the box? I want you to try and calculate what this value is, and then I'll give you another. Say, you can pause the video to figure out an answer, and then come back and look at the result. Okay, the answer to question 2 is 3. How do I figure that out? Well, by definition, the energy per unit volume is equal to this expression. And so what I need to find the total energy is I got to take the energy per unit volume and multiply it times my volume, and that volume is the length, width, and height of the volume that contains my electric field. And if you do that, you get 3.67 times 10 to the minus 6 joules. All right, let's talk about momentum. How do I get momentum out of the electromagnetic radiation? Well, to do that, I need to describe the energy flux in another way. We usually refer to it, if I represent it in this format, we call it the Poynting vector. And I think I've drawn that expression wrong. The magnitude sign should be taken away from the E and B, cross product of E and B. This cross product in E and B will give you the direction of the wave, so we call it the Poynting vector. Well, that gives me the energy flux. Well, if I divide the energy flux by the velocity of the wave, which is c, I get what is called the momentum flux. This helps us calculate the momentum of the electromagnetic wave. Well, this momentum flux has units of pressure, so it's usually referred to as radiation pressure. Electromagnetic waves can interfere with matter. And, well, why does it interfere with matter? Well, matter is made up of neutral atoms, and neutral atoms neutral atoms contain charges. These charges will oscillate when they are exposed to sinusoidal electromagnetic radiation. Since these charges are accelerating, they will re-radiate in all directions. The energy of the re-radiation comes from the original radiation, so the original radiation energy will be reduced. And it gets reduced several ways. As it comes in, the original radiation will accelerate the charge, and then the charge radiates in all directions. So now that initial piece of radiation is now radiated 360 degrees in a sphere around the The re-radiation radiates 360 degrees around a sphere, ideal spheres, out, and so the intensity gets definitely reduced. And then the other effect that can happen is if it re-radiates in the direction of the original radiation, the propagation direction of the original radiation, the electromagnetic radiation in that direction will have to add together to get the net electromagnetic radiation. And if they add together to where the magnitude decreases, the intensity will go down even more. So one of the ways to see this is a polarizer. And in the chapter, they have extensive talk about polarizers. So we have this question 3, and they want to know in which situation will the light bulb light up, situation A and situation B. A and B are antennas, and they will accelerate the electrons parallel to that antenna. I'll give you, say, 30 seconds to, well, what you should do is pause the video and come up with an answer. All right, so what's the correct answer? For antenna A, the acceleration of the electrons will be in the direction of the red arrow. Then, since they're electrons and the radius r is outwards towards the polarizer, your electric field direction will be parallel to the acceleration of the electron, and then this electric field will hit the polarizer. What happens is, since this electric field is parallel to the polarizer directions, or parallel to these lines, it will cause those electrons to accelerate and re-radiate, and cause what we refer to as scattering or re-radiation from the electrons in the polarizers, and that is going to take away some of the initial energy from the original radiation. So there's not enough radiation to get to the wire and accelerate the charges so the light bulb is bright. Now if we look at B, B has the same acceleration as electron A. It produces a same electric field direction, but since the electrons cannot be accelerated perpendicular to the slats, you get no re-radiation. So the initial radiation that hits the polarizer is transmitted through the polarizer, just like we've talked before, and then it energizes the electrons in the receiving antenna and lights the bulb brightly. So the answer to this question is B. So I'd like you to answer question 4. If you were paying attention to the answer of question 3, I think you should get the answer quite quickly. So pause the video and come up with answer 1, 2, or 3. And when you got your answer, replay the video, and we'll talk about the answer. All right, so the answer for 4 is, let's see, radiation cannot go through the foil strips. Well, we know that's wrong. Re-radiation by the electrons in the foil decreases the energy that reaches the bulb. The re-radiation electric field is in the wrong plane. Well, I know it can't be 3 because the electrons could go parallel to the foil, so it's got to be 2. The re-radiation by the electrons in the foil strip decrease the energy that reaches the bulb. Okay, so we're at the end of the podcast. You should have a better understanding of sinusoidal electromagnetic radiation. how energy and momentum is stored in electromagnetic radiation, the effects of radiation on matter, and polarizers. So we're going to have a Google Hangout at 10 a.m. Eastern 10 a.m. Eastern Standard Time. In order for me to get you into the Hangout, I need to know your Google Plus account. So I want you to email me your Google Plus account, your email associated with that Google Plus account, or you can friend me to put me in one of your circles, and then I'll show up that, and then I'll know the email address. So you can do one of those two steps. My email address on my Google Plus account is taduman@yahoo.com. All right. I'll see you at the Hangout. Bye.